Okay, now we're going to talk about continuous growth and decay. And when we talk about continuous growth and decay, we're going to use the formula y is equal to p e to the RT. P is your initial amount. Sometimes it's labeled as A naught as well, which is the same thing. Some people use different letters, and just know that whatever is in front here is your initial value no matter what the letter is. R is going to be the rate of increase or decrease. You're going to be able to tell if it's increasing or decreasing depending on what R is. If R is positive, it's going to be increasing. So when you graph it, it will go up like this. And when R is less than 0, it's decreasing, which means it's going to look like this. And what happens is when you put that negative in front of the R, it's going to flip the graph over the y-axis. So instead of coming up like this, it's going to come down like this. It's going to flip it over the y-axis, which is why when R is negative, it's decreasing. Because the negatives, if you think back to your rules of translation, negatives flip things over either the y-axis or the x-axis. Those are our reflections. Okay, now we have a new function called the logistic growth model. The logistic growth model is similar to the exponential function. The formula for logistic growth model looks like this. A, B, and C are just numbers. They're just real numbers. And then your x is your independent variable, and your f of x is your dependent variable. And this is very similar to an exponential function in the sense that it has a horizontal asymptote at y equals 0. And just like an exponential function, when it goes to the left, if it's increasing and it goes to the left, it's going to flatten out, then it's going to come up, pass over the y-axis, and it's going to increase quickly. Now this is where it changes, and it's not the same as an exponential function. Exponential functions would continue to grow very quickly, but with the logistic growth model, then at some point it starts to level out. So it continues to grow, but it reaches a point in which it levels out. Now that point in which it levels out is called the carrying capacity, or another way to say it is limiting value. And that's always going to be represented by your value of C in the equation. This value of C is your carrying capacity. That's where it's going to level out. So this equation here of where it flattens out going to the right is going to be y equals and then whatever your value of C is. Now we have a point here in which the graph turns from concave up. Here is concave up, and then here is concave down. At that point where it turns from concave up to concave down, this is what's called the point of maximum growth. And that's where it's going to be growing the fastest. And in order to find what that point is, it's just a formula. To find the x-coordinate of that point, you take the natural log of whatever the a is in your formula over the value of b. And then the y-coordinate would be whatever your c value is divided by 2, because it's half that height of that limiting value or that carrying capacity. Okay, so let's do the first example. It says find f of 0 and f of 3 and round to the nearest tenth. And it gives us a logistic growth model. C is going to be 200. A is going to be 9, and B is going to be 2. For part A, we have to plug in 0 and then plug in 3. If I plug in 0, that's going to give me 200 over 1 plus 9e to the negative 2 times 0. When I take e to the power of 0, that's just 1. And then 1 times 9 is 9. And then when I add that to the 1, that gives me 10. So this big mess right here is equal to 10 because this is equal to 1. So I get 200 over 10, which gives me 20. Now I'm going to do this for f of 3. When I plug in 3 for x, I get negative 2 times 3, which gives me negative 6 in the exponent. Now this is considered our exact value. The question is asking us to put it in as a decimal to the nearest tenth. So if I want an approximate value, I have to put this in on my calculator and get a decimal value. And make sure when you put this in on your calculator that you put it in like this. You do 200 divided by, and then you put parentheses around everything. You raise it to the power of negative 6. That's how you want to put it in on your calculator. And make sure you use the negative and not the minus for that negative 6, because otherwise you'll get an error message. When you put that in on your calculator, it says round to the nearest tenth, so that means 1 decimal place. So I have 195.6. So this would be f of 3. In part B, it says find the carrying capacity. So that means as x goes way far out to the right, where does this graph level out at? That's my value of c. So that's going to be 200. In example 2, we have a function written as a times b to the t, where a is 1.11 and b is 0.15. And we want to rewrite this in terms of a base e exponential function. Since these are the same, my initial values, what I'm trying to do is find a way to make ek to the t the same as 0.15 to the t. So I need to figure out what that value of k is that would do that. I can't change e is a constant, just like 2 or just 5. E is a constant, I can't change that. But I can rewrite k so that e to the k is equal to 0.15. So I got to figure out what would k be so that e to the k is 0.15. So in order to do this, I'm solving for something in the exponent. This is an exponential equation. I'm solving for k in the exponent. And when I do that, what I need to do is isolate my exponential and then put it in log form. So my base is e, so I'm going to use natural log. Log base e of 0.15 is equal to my exponent, which is k. And then if I want to write it with ln, because it's natural log, I can. These are the same. Log base e is the same as natural log. So what I would do is I would put this in the calculator, and it says round it to 4 decimal places. So I'm going to find the natural log of 0.15. And I'm going to round it to 4 decimal places. That's going to give me approximately negative 1.8971. Now notice that this is negative. When we have it in this form, if it's decreasing, our rate, or in this case, it's calling it k instead of r, but that k should be negative if it's decreasing. So my final answer is going to be 1.11 e to the power of negative 1.8971 t. So these two equations are equivalent. We just rewrote it 2 different ways. This way I know it's decreasing because my b is less than 1. Right, here's my b. It's less than 1, so I know that should be decreasing. And when it's in this form with my base e, I know it's decreasing because this is negative. Okay, example 3, we have another logistic application. It says the population of a fish farm in T years is modeled by the equation, and then it gives us the logistic equation. Rounded to the nearest fish, what is the initial population? So I'm supposed to plug in the time is 0, because that would be, time 0 would be when we have our initial population. Okay, and figure out what that initial population was at time 0. So I need to find P of 0. This would give me my initial population. So I have 750 over 1 plus 9 to the power of e to the negative 0.5 times 0. This whole thing is equal to 1 because e to the power of 0 is 1. So I get 750 over 1 plus 9, which is 10. So when I take 750 divided by 10, I get 75. So this is saying we start at 75 fish. If I were to graph this, that's where it would cross here at 75. It would level out going to the left at 0. It would come up, and then it would flatten out at C. In this case, our value of C is 750. So this would be our carrying capacity. So it's pretty much going to max out, or come close to maxing out, at 750.